Hello everybody, my name is Richard Berger from the University of Technology in Graz, and in this video I would like to show you a bit about how adatoms can influence the properties of F4TCNQ adsorbed on the gold 111 surface. So why are adatoms even an issue for the adsorption of molecules on metal surfaces? Now, the thing is that usually we think of molecules adsorbing on idealized perfect surfaces, and we think that these molecules order themselves into an ideal purely molecular monolayer. And this might be true for many combinations of metallic substrates and organic molecules. But there are also many reports that adatoms from the metal substrate can incorporate within the adsorbed molecular adlayer. And this then forms some kind of ordered two-dimensional metal organic monolayer adsorbed on the surface. And one system that is very well known for incorporating adatoms within the molecular adlayer is F4TCNQ adsorbed on the gold 111 surface. Now, since for this system there is so much experimental and also theoretical evidence that the gold adatoms are part of the F4TCNQ adlayer, we found it would be interesting to know why the adatoms are in the adlayer and also what their impact is on the physical properties at the interface, such as the work function or the adlayer metallicity. And to answer this, we compared the experimentally very well-known system with adatoms to a system without adatoms, and we asked ourselves why the structure with adatoms is the physically stable one. And when we talk about the stability of a phase, we must know about the energy of that phase. And therefore, we will now split up the adsorption process into several sub-steps and will associate an energy with every step. And the first thing to think of is, where do the adatoms even come from? And here we make the assumption that we extract the adatoms from the bulk phase. And this is energetically, of course, the most costful way to create an adatom, because we have to provide the full adatom formation energy before a molecule can adsorb on the surface. But in this way, the bulk can also serve as a natural adatom reservoir. So while the adatom formation costs energy, with the adsorption of the F4TCNQ molecule on the surface, the whole system gains energy, namely the adsorption energy, which is defined as the energy difference between the final state, where the F4TCNQ is adsorbed on the slab with the adatom, and the initial state made of the slab plus one bulk atom and the F4TCNQ molecule in vacuum. So if the incorporation of adatoms within the adlayer would increase the adsorption energy of the molecule so much that it could make up for the formation energy of an adatom, then the molecules could extract as many adatoms from the bulk as they would need to form the energetically most ideal adlayer. And that's exactly what happens when F4TCNQ adsorbs on the gold 111 surface. Because when we compare the case with adatoms to the case without adatoms, we find that the adsorption energy in the case where the adatoms are present is so much bigger than the adsorption energy without adatoms that this even makes up for the energy needed to extract the adatom from the bulk phase. Now, we can also split up this adsorption energy into different contributions. And for the case without adatoms, we find that almost the whole adsorption energy is due to an increased van der Waals energy when the molecule adsorbs on the surface. Now, with adatoms, there is a comparable amount of van der Waals energy, like in the case without adatoms. But the significant part of the whole adsorption energy with adatoms is because the F4TCNQ molecule is covalently bound to the adatom. And with this, we can already answer our first question, namely, why are the adatoms incorporated within the adlayer? And the answer simply is because they covalently bond to the F4TCNQ molecules. And this brings us to the second question, namely, what is the influence of the adatom on the interface properties? And to learn a little bit more about this, we project the density of states of our systems with and without adatoms onto the molecular orbitals of the adsorbed F4TCNQ. And what this gives us is just the contribution of the molecular orbitals of F4TCNQ to the total density of states for all possible energies. Now, with adatoms, we find that all hybridized states associated with the former lowest unoccupied molecular orbital of F4TCNQ fall below the Fermi energy, which means that with adatoms, the former lowest unoccupied molecular orbital gets fully filled. And this goes hand in hand with the fact that we have a very low density of states of the add layer at the Fermi energy, which means that the metallicity of the add layer is rather small in that case. On the other hand side, without adatoms, we find that the former F4TCNQ lowest unoccupied molecular orbital only gets half filled, and therefore also the add layer density of states at the Fermi energy is high, which means that without adatoms, we have a high add layer metallicity. So this shows us something rather counterintuitive, namely that when we incorporate the metallic gold adatom within the molecular add layer, we actually decrease the metallicity of the add layer. And we also find an increased occupation of the former lowest unoccupied molecular orbital of F4TCNQ when the adatoms are present. Now, another interface property that is significantly modified by the adatom is the charge transfer between the molecule and the substrate. Now, the charge transfer from the substrate into the lowest unoccupied molecular orbital, which we have already seen on the previous slide, is called the forward donation, and it is shown here by the green arrows. But there is also charge transfer from the cyano groups of F4TCNQ towards the substrate, which we call back donation, and it is illustrated here by the blue arrows. Now, of course, the forward donation is much bigger with adatoms because there we see a fully filled lowest unoccupied molecular orbital, whereas without adatoms, it is only half filled. But the back donation from the cyano groups of the molecule towards the substrate completely compensates the forward donation when there are adatoms in the add layer. Whereas without adatoms, the back donation is smaller than the forward donation, meaning that there is a net charge transfer from the substrate towards the molecule. And this net charge transfer that we only see without adatoms causes a dipole across the interface. And we will see that this bond dipole, as we call it, has a significant effect on the work function at the surface. Now, in order to determine the work function modification by the adatom, one must know that there are three different dipoles at the interface, adding up to increase or decrease the work function. And therefore, right here, we illustrate the single contributions of these three dipoles to the overall work function modification. First of all, we have the contribution of the bond dipole due to the net charge transfer across the interface that we just saw on the previous slide. Then there is the molecular dipole that arises simply from the asymmetric geometry of the molecules at the surface. And last but not least, there is the dipole of the slab, but this only contributes a little bit in case there is an adatom at the surface. Now, first of all, in both cases, with and without adatoms, we find that the molecular dipole decreases the work function. But with adatoms, we have much less net charge transfer across the interface because the charge back donation from the cyano groups cancels with the forward donation into the lowest unoccupied molecular orbital. And therefore, the bond dipole that is caused by the net charge transfer is very, very small when we have adatoms at the interface. And with this, we find that while without adatoms, the work function would actually increase, in the case with adatoms, we decrease the work function at the interface when F4TCNQ adsorbs on the surface. And this brings me to the conclusions of this talk. Now, first of all, we found out that the adatoms add so much covalent bonding energy to the add layer that this even makes up for the energy needed to create an adatom and still forms the energetically most favorable structure. Then we also saw that the incorporation of adatoms in the ad layer decreases the metallicity of the ad layer. And last but not least, we found out that the adatoms decrease the work function at the interface when F4TCNQ adsorbs. And with this, I would like to finish the talk and thank you for your attention.